Now, let's go on that field trip again to the big field of snow where there's that frictionless pond. We're going to lay that same standard meter stick down, but this time we're going to drive a stake, a pivot through that, the end of that meter stick, and that's a special pivot that is frictionless. Okay, we've polished it and we've greased it so that there's no friction there. Now, if we push on that meter stick with two forces, each force 50 newtons, you know that those two forces are going to cancel in a linear sense. 50 to the right, 50 to the left, that adds up to 0. And yet when we're talking about rotation, you can see that it's not a tie. One of those forces is going to be more effective in causing rotation than the other one. Which one is it? Yeah, the one that's further away from the pivot. Okay, you've all experienced this when you're trying to get a nut off of a bolt and it's rusted on, and so you're pulling with your wrench. So what do? You go and you get a bigger wrench so that you can pull further away from the pivot. And if that doesn't work, you get a pipe to put on the end of that big wrench and you pull, way out here. And if you're like me, you break the bolt right off and have to start over. So the further away from the pivot, the more effective a force is in causing rotation. And yet that's not everything. Because if I were to push here and here, F2 is still applied further from the axis, from the pivot point. And yet, how much torque, how much rotation am I going to get out of F2? None. That's a dumb guy force, okay? If you come to a revolving door, I'm not sure they have those in Montana, but in some places they have those. You come to a revolving door and you push like this, they go and get the authority. And you get to talk to somebody, a very friendly person, okay? Now, what we see here is that the angle at which you apply that force matters. How far you apply it from the pivot matters, and the angle at which you apply it matters. Now, in general, what we have to do is we have to define this vector r, the position vector, that starts at the pivot and goes to where the force is applied. The next thing we have to do is define this angle, and listen carefully to my words. This is the angle between the direction of r and the direction of f. Don't ever say it's the angle between r and f, because that's going to make you want to use this angle here. It's the angle between the direction of r, which is towards the ceiling, and the direction of f. So if r is towards the ceiling and f is that way, it's this angle here. Okay? Now, if we define that angle and that position vector, what we find is that the torque, we use the Greek symbol tau, the torque is equal to the magnitude of the position vector, the magnitude of the force, times the sine of the angle between them. Now that sine is biggest when theta is 90 degrees. And the torque for a given position vector and a position force is biggest when they're 90 degrees to each other. Okay? Now, in practice, in 90% of the homework problems, 90% of the exam problems, what you will have is a case where the force and the position vector are already perpendicular. Okay? If that's the pivot and that's the force, that's the position vector. That's what it usually is. And in those cases, it's just very simple. It's just the force times the distance to the pivot. That's the torque. The force times the distance to the pivot. But they have to be 90 degrees to each other. Now, in this case, that would be 3 meters times 200 newtons, or 600 meter newtons. Now technically I could call that 600 Newton meters, but I don't. I never do. I always call it meter newtons, because Newton meter has a different connotation. What's a Newton meter? Newton meter, Newton meter, Newton. Joule. Okay? That's the unit of energy, and this is different than energy. This is a different concept. And so I will always call that a meter Newton. Or in America, what do we call them? Foot pounds. Foot pounds. Instead of meters, we have foot, and instead of newtons, we have pounds. Okay. Now again, I can't say this enough. A torque is a force times the distance to the pivot, but they have to be perpendicular to each other. So what if they're not? Well, we have two options. The first option we call the useful force method. We use in this method all of the position vector, but only the part of the force that is perpendicular to that position vector. We break up that force into two components, one that is perpendicular to this r vector, and one that is parallel to this r vector. Now you can think of these two components as forces that are applied right there. In other words, think of these as two strings, one pulling to the left and one pulling straight up, right there, straight up. If I'm pulling right there, straight up, is that going to cause rotation? No or heck no? Heck no, yeah. So this is not giving me any rotation. This is the only part that's useful for causing rotation. Now if I use a little math, trig, actually geometry, this angle has to be that angle by opposite interior angles. And now I use a little trig. This is my right triangle. So this is the opposite side. And that's going to be the force times the sine of that angle. Now if you look at my definition of torque, there's the force times the sine of that angle. That's the useful part of the force. That's the perpendicular part of the force. So we use all of the distance and only the part of the force that's perpendicular to the distance. Okay? Again, torque is a force times the distance, but they have to be perpendicular to each other. And that force is perpendicular to that distance. Now, there's another method. Oh, Greg, don't give me another method. I don't want two methods. Just give me one method. You're going to find in this week's tutorial that this method makes half of all the problems trivial. And the other half of all the problems really, really hard. So we do need another method. And the other method we call the lever arm method. And in this method, we do exactly the opposite of what we just did. In this case, we're going to use all of the force, but we're only going to use part of this position vector, the part that's perpendicular to that force. Now, to use this method, we extend the force in both directions forever, and we call that the line of action. And we say that this force is acting along the line of action, along that line. And then we find the distance that starts at the pivot and comes in perpendicular to that line of action. Now looky here. That force is perpendicular to that distance, and that's going to give us our torque. Now if we do a little geometry again, this angle here has to be how big compared to theta? Well, it's got to be theta, right? Okay. And that means that this blue line is going to be the hypotenuse. There's my right triangle. It's going to be the hypotenuse r times the sine of the angle because it's the opposite side. Now, if I look at my general definition of torque, F r sine theta, that r sine theta is just the lever arm. So the total force times just the part of the distance that's perpendicular to that force gives me the torque. Now again, half of the problems will be trivial with this approach and very complicated with the other approach.